Hey everybody, Dr. A here, and in this video we're going to be exploring an example of applying the dot product. So let's go ahead and get started. In the given information, we're being asked to compute the angle between the two pipes. And so here we have this three-dimensional figure. Let's take a look at what we're given. We have this positive x-axis here, we have a positive y-axis here, and then we have this positive z-axis coming up. Now, along the positive y-axis, we have this pipe segment here, and we can think of this as pipe AC. Okay, so the origin is C, and the end of that pipe along the y-axis is point A. And then we have a second pipe segment that is angled downwards and kind of backwards from A. So we have this pipe segment here, the second one, AB, that again is angled down. So we have a negative Z component here. And specifically it's angled down where it has a 1.5 foot drop from the XY plane. That's this dimension here. And it's got a slight angle backwards as well. And the way we can visualize that is we see that that first pipe segment AC is 2 feet long, but then we have a 1.5 foot dimension from the x-axis to the end of this pipe. So you can tell this kind of angles back to where you lose 6 inches or half a foot dimension here. And then it extends in the positive x direction by 1.5 foot. So this point right here in red is a projected point. So I took that point B and I projected it up to the XY plane so we can kind of see the dimensions a bit more clearly, okay? And again, this 1.5 feet is a Z dimension, which is the distance from the XY plane down in the negative Z direction to point B, which is the end of that segment AB, okay? So what we're looking for is this angle theta in between these two pipes. So how do we get that? Well, that's where we use the dot product, okay? So let's go ahead and write solution. And let's think about our general relationship for the dot product. Well, what the dot product says is we can take two position vectors, okay? Let's say we have the position vector AB, and we can dot it with the position vector AC, and what that's going to equal to is the magnitude of the position vector AB times the magnitude of the position vector AC times the cosine of the angle in between those two position vectors. So that's the general relationship, and if you're a little rusty on that, you can go back and rewatch a previous video where we give some background information on this. So what we do from here is we can rearrange this, and we can say that theta is going to be the arc cosine of this rearranged. So that'll be RAB dotted with RAC divided by the magnitude of RAB times the magnitude of RAC, okay? And so that's the general relationship we have from our background information. Now, the key to remember in this process is that the tails of these two position vectors have to meet each other, okay? The tails have to be incident at each other, which means that the tail of RAB and the tail of RAC has to be point A, right? So if I use my original figure to help me kind of do a little bit of sketching, what I'm going to have here is this position vector, RAC, and notice that the tail is at A and the head is at C. And then I'm going to have a second position vector along this second pipe segment right here. And this is RAB, okay? Again, with the tail at A and the head at B. All right, so that's the key kind of concept, mathematical concept we have to remember, is that the tails meet at the same point. All right, now what I have to do at this point is really just define these position vectors, okay? So really what the work that goes into this is really more so on getting these two position vectors. Then we can put it all together with this dot product relationship to get theta, all right? So let's go ahead and do that. Let's get each position vector. And we remember, whenever we define a position vector, we always take the coordinates of the second point, which is where the head is of the position vector, minus the coordinates of the first point, which is where the tail is. So you can think of this as coordinates of the second point minus coordinates of the first point, or you can think of this as the coordinates of the point you're going to minus the coordinates of the point you're coming from. Another way you can think of this in your head is coordinates of the head of the position vector minus the coordinates of the tail of the position vector. I don't know why I just like had a little brain freeze right then. But either way, different ways to think about that, okay? So let's go ahead and define these two position vectors. I'm going to start with RAB. All right, so RAB, of course, is going to be XB minus XA times I plus YB minus YA J plus ZB minus ZA K. All right, so let's go one at a time. And again, we're starting with AB. So I'm looking at this vector right here. All right, and I'm going to start with the coordinates of B. Okay, so RAB. What is X sub B? Well, I'm looking at point B, and its distance from the origin is 1.5 feet. Okay, remember we said that point B projected up in the XY plane is going to be 1.5 feet away from the origin. Okay, so that's going to be written as 1.5 feet. And then minus XA. What are the coordinates? What's the X coordinate of point A? Well, that's along the Y-axis, right? So that's just going to be minus 0, and we'll have an I there. Okay, what about the Y coordinates of B? Well, the Y coordinate of B is this 1.5 feet. Okay, we said that, again, point B projected up to the XY plane is here. That's 1.5 feet away from the X-axis in the positive Y direction. So that will be 1.5 feet minus YA. What is the Y coordinate of this point A? Well, that's this 2 feet. Okay, so minus 2 feet J. And then we're looking at the Z coordinates. The Z coordinate of B is negative 1.5 feet because we're kind of angled down in the negative X direction. So that'll be minus 1.5 feet minus ZA. What's the Z coordinate of A? Well, that's just 0 because we said, again, point A is lying along the Y-axis. And so that'll be times a K. And so we can write this as RAB equals 1.5 I minus 0.5 J minus 1.5 K. And we can bundle that up with units of feet here. Now, similarly, I need RAC, right? So RAC is going to be XC minus XA, I, plus YC minus YA times I, plus Z sub C minus ZA K. All right? And so what is the X component of point C? Well, that's just 0. In fact, point C is at the origin, so all of its coordinates are 0. So really, we just need to subtract, we just need to say 0 minus each of the coordinates of A. So actually, this becomes quite simple. So we're going to say RAC equals 0 minus 0 I plus 0 minus 2 feet J plus 0 minus 0 K, and we'll get RAC should just be negative 2j with units of feet there. And so now I've got my two Cartesian position vectors. Here's RAB and here's RAC. Now, before I enter into this relationship to get theta, I'm also going to need those magnitudes, okay? So let's go ahead and get those. We'll go ahead and say the magnitude of RAB comes from applying the Pythagorean theorem to position vector RAB. So I'm going to go ahead and do that in my calculator. Hopefully we're comfortable with executing the Pythagorean theorem. We're going to say 1.5 squared, and we're going to say add that to 0.5 squared, and then we're going to add that to 1.5 squared again, square root all of that, and you should get a magnitude of 2.18 feet. And then, of course, if I want the magnitude of RAC, that's just going to be 2 feet. How do I know that? Well, I square the -2 and it becomes +4, but then I take the square root of that, so I'm left with a +2 feet. So those are my magnitudes that are going to go in this denominator. Now I need to execute the dot product here. Now, how does the left side of the dot product equation work? Well, you just directly multiply corresponding components, okay? And so when I piece this all together, what is that going to look like? Well, I can say theta equals arc cosine of, and in that numerator, I'm going to multiply corresponding components of RAB and RAC down here, all right? So what are the product of the x components? That's 1.5 times 0, right? Because RAC only has a j component. So here I can say 1.5 times 0 plus, and I'm going to say negative 0.5 times -2. So negative 0.5 times -2. And then I'm going to say plus negative 1.5 times 0. Again, RAC only has a j component, so plus negative 1.5 times 0. And remember, these still have units technically, right? They all have units of feet. Okay, so I can put feet everywhere there. Then all that's going to be divided by 2.18 feet times 2 feet. And I'm going to bundle this up in a parentheses. And we see, a couple of these terms, very quickly cancel. So when I punch this through in my calculator, I'm going to say arc cosine of negative 0.5 times -2. So that comes out to be positive, divided by 2.18 times 2 in that denominator. Make sure you're careful with your parentheses. But finally, I get 76.74 degrees as my answer. So again, make sure you watch your parentheses. Make sure your calculator is in degree mode if you want theta in degrees. And that concludes this example. So if you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.